Hello everyone. Today, in the structural analysis program, I will provide information on how to perform a performance analysis of a 5-story residential building constructed in 1980. According to the 2018 Turkish Building Earthquake Code. First, we need to know the performance levels in our code to convey this information. As seen in our code, there are 4 performance levels. These are the continuous use, limited damage, controlled damage, and prevention of collapse performance levels. Does our code specify whether the building is existing, new, or high-rise? First, if we start with the continuous use performance level, this performance level requires different performance targets at different earthquake levels depending on the design of your building. First, if we start with the continuous use performance level, here, this performance level is the condition where no structural damage occurs in the building's load-bearing system elements, or the damage remains negligible. The limited damage performance level corresponds to the damage level where, as the name suggests, limited damage occurs in the building's structural elements, meaning that the nonlinear behavior is kept to a minimum. In controlled damage, it refers to the performance level corresponding to a damage level in the building's load-bearing system elements that is not very severe and is mostly reparable. The purpose of this performance level is actually to ensure life safety. Our final performance level is the prevention of collapse performance level. At this performance level, the building's structural system elements have sustained severe damage to an advanced degree, corresponding to the performance level just before collapse. In other words, the partial or complete collapse of the building has been prevented. And, based on the performance levels in the regulation, as seen in the table here, is it a new construction, or a high-rise building, or is it an existing building? Accordingly, some performance targets are required, and these are, of course, required at different earthquake levels. If we look here, for example purposes, for new or existing high-rise buildings, that is, for option B here, if our earthquake design class is 1, 2, 3, 3A, 4, or 4A, you can see the earthquake levels on the left. On the right, there are the performance targets and evaluation approaches. For example, under the DD1 earthquake, the performance target is the prevention of collapse, and the evaluation approach should be based on deformation. This is how it is required. In other words, 3 different performance targets are required. It is required according to DD2 and according to DD4. Now, as we mentioned, we have 2 different evaluation design approaches. One of them is force-based analysis. So, the force-based analysis we use when we solve our normal structures statically. In other words, design based on strength. Here, it is specified as DGT. And there is also deformation-based analysis. In deformation-based analysis, it is not a force-based analysis method, so how is it not considered here? In the deformation-based analysis, the deformation graphs of the relevant reinforcements are examined, and calculations are made based on these. Therefore, deformation graphs are very important here, and reinforcements are crucial in deformation-based analysis. For example, since such structures will be newly constructed, a preliminary design under the DD2 earthquake is desired, meaning that our force-based analysis or design based on strength is required. Then, for example, it is required to look at the analysis according to deformation for DD1. In this way, we have 2 different design approaches. These are important. Apart from that, let's now show the performance steps sequentially on the program. Yes, as can be seen, our structure is a 5-story residential building, an existing structure. And I will Perform the performance calculations, assuming that we do not have the reinforcements. If we have the reinforcements, then I will explain how to perform a performance analysis for an existing structure in the next video. Now, let's assume that we do not know the reinforcements. In such situations, what approach should we follow? First, we need to determine the reinforcements to be able to perform your performance analysis. Since we do not know these, we will approximate them. So, we went to the structure on site and saw it. Our structure is standing under vertical loads. We will design the structure based on vertical loads. Since it is standing based on vertical loads, we will place the reinforcements accordingly. In other words, we will nullify the earthquake. We will determine a reinforcement by setting the earthquake to 0. Yes, before nullifying the earthquake, we need to enter the material values obtained from the core results into our structure. It is beneficial to perform this process initially. Now, here we have our performance section. As you can see, we come here and here. Since it is an existing structure, we need to define a material for all floors and all elements ranging from E2 to E9. Because they are currently of E1 material type, the E1 material type is used for newly defined structures. Yes, now we will define our E2 material. I am choosing this option here to assign it to all floors. And yes, he stated that concrete is a forest element. Here, I will enter the material properties. Based on the core results, I need to write down the concrete class that came out here. Yes, here, I am assuming that C15 concrete is used. And I am also assuming that our reinforcements, RS220, and our stirrups are taken in the same way. After determining these properties, I am taking the floor plan for the window here. And since the entire floor option is already selected, the program has now taken the entire building as E2 material. Yes, when it is accessed, we can already view it as E2 material. From here, now we have completed our material assignment. After completing these steps, look here, we come to the general information section of the building. Here, we need to enter our general information about the building. As seen here, our earthquake is taken as 0. We are specifying this. Apart from that, the readhesis system's narrowness coefficient is irrelevant since the earthquake is already taken as 0. However, in performance analysis, our current priority is, of course, to determine the reinforcement. However, in the performance analyses conducted, the R value must always be taken as 1. Even if you enter a different value here, the R factor in the performance value will be taken as 1. If you are only going to define the reinforcement elements, they will be defined with a material since they will be new elements, and you need to enter R as 4 for the other one, because it is beneficial to design their reinforcements according to 4. Other than that, no matter what value you enter for R, there will be no change. It is beneficial to enter it directly as 1 here. Therefore, the other options do not matter right now because we have nullified the earthquake. Here you can see the importance factor of the building. Since it is already a residential building, we selected 1. However, even if you enter a different value in performance analyses, it will be considered as 1 according to the regulation. You can find the item in section 15.4.2 of our regulation. The I value is as follows. Apart from that, we also have a general live load reduction factor. For residential buildings, this is considered as 0.3. I can say these things. The information here is generally related to earthquakes. These are not important at the moment. And of course, here, after determining this, we come to the performance section here, and we have our performance options section. It is also beneficial to check this option, and you can select the design code based on the period when the building was constructed. I am selecting the 1975 regulation because I assumed it was built in 1980. This is important. Apart from that, while performing a normal performance analysis, the options here will be very important. Before directly moving on to the analysis and determining the directions, I would like to briefly mention what these options mean here. First of all, if you want to calculate the performance of your structure, you must definitely check this box when performing a performance analysis. When you check this box, the program will understand that you want to perform a performance analysis and will carry out the performance analysis accordingly. If you do not check this box, you will not be able to perform a performance analysis. Therefore, you must definitely check it. As for the options here, our first option shows us the building information level coefficient. Of course, we cannot determine all elements in the field in terms of reinforcements, but we have the chance to determine some elements with cores and others with reinforcement detection devices, and there are certain ratios for these. For example, there is a certain ratio for columns and a certain ratio for beams. Based on how well we meet these ratios, a building information level coefficient is defined for us by our director. If we have comprehensive data, we can enter this value as 1. If we do not have comprehensive data and know less about the reinforcement, then we need to enter this value as 0.75. I am entering this value as 0.75. When we look at our other option, it also appears as the reinforcement anchorage length capacity factor. If we do not have sufficient anchorage, the program performs the necessary reduction by taking this into account. If the reinforcements are not adequately anchored, you enter the corresponding ratio. Accordingly, it performs the reduction proportional to the entered coefficient. Here, our available option is referred to as the bilinear vertical load moment factor. With this option, it performs moment reduction based on the principle of redistribution. For example, I will consider this as 0.85. For now, I will consider this value here as driving. This is actually the motion load reduction factor considered in an earthquake. Here, we had already entered it as 0.3 in the general building information at the beginning. We can enter the same value here. And here we also have the option for this beam reinforcement. Realization rate. This is also available for columns, and they are also found in the walls. What does this show us? For example, let's say you used 14 mm reinforcement in the beams in the project. This 14 mm reinforcement has become a 12 mm reinforcement due to corrosion. This actually ensures that it is taken into consideration here, since the area of the reinforcement decreases accordingly. If you enter the reduction as a ratio here, the program takes into account this reduction due to corrosion in the inputs, and you can obtain a more realistic result. This is important in this regard. If we look at the options on the right, our first option is that when this control is not ensured, the relevant element is designated as a brittle element, and accordingly, the regulation requires the strengthening of this element, such as in our second option, there is a cracked section analysis, and an analysis option according to the cracked section. Here, it is beneficial to select the cracked section option accordingly. The lugit dips are reduced, and the calculation is made based on this. Our other option is dead load, construction stages analysis. This option becomes particularly important if you are going to add an additional floor to the structure. So, it becomes important not when this option is selected here, but when the second option is selected there. Why is it important then? Because you have an existing structure. You will add a new load to it. A new floor will be added on top. It will create an extra earthquake load on the existing structure. Therefore, conducting the analysis step by step is very important in relation to the topic. And therefore, in such situations, it is beneficial to check this option. Since the first two options are particularly important, we can continue to check the other options by marking these two options as well. Our other options are more related to reinforcement. As you can see, there are two options. These options are related to the loading walls. The difference between the two options on the left and the two options on the right is as follows. Here, it explains the strengthening walls that use the existing columns as the header of the panel. Here, it explains the strengthening walls where the header region is created within itself. And should these strengthening walls be connected to these beams with root, or should these beams be broken to form a strengthening wall? How should it be done? We are expected to choose one of these two options. The same options are available here. However, as I mentioned here, the program considers the existing columns as the header of the panel wall. In this case, the situation takes into account creating the title within itself. That is the difference. Other than that, there is a vertical load logic option here in this option. We expect the jackets to be more effective during an earthquake if a column is jacketed, and we expect the columns to bear more of the vertical loads if the column is solid. Therefore, usually, the first option selected is that our column is active and our jacket is passive. However, in some cases, if the columns are damaged or have significant damage, then the jackets may also need to bear these vertical loads. The jacket may also need to contribute to bearing the vertical loads. In that case, here, we need to select the column passive, mantle active option. In other words, we need to choose the third option. It is beneficial for the option below to be checked. Here, it performs a capacity check, although it does not contribute to the analysis based on deformation. It does contribute to the capacity analysis. If the amount of normal force in the column rises to an abnormal level, meaning it becomes excessively high, then this option activates when it is checked, and it absorbs the excess load, the vertical loads, which provides us with an advantage in capacity control. Apart from that, we have our concrete calculation option according to the necessary section here. If you think that the provided reinforcement ratio is much less than the minimum reinforcement ratio, then it would be beneficial to reinforce it. Here, we can also identify our damaged elements. In the program, I will show you how to determine them. If there are damaged elements, we identify them in advance. And here, the options for slightly damaged elements, moderately damaged elements, and heavily damaged elements are displayed here. There, contributions to the calculation are taken into account. If there is minor damage, the contribution of that element is considered 100% in this analysis. If it is moderately damaged, it is considered at 70%. But if it has severe damage, then that element is not considered in the calculations at all. The contribution from it is not being considered. And as heavily damaged, we need to mark this in the program, of course. For example, how do we indicate this? If we go to the floor editing section, of course, I need to click on this performance option again. Yes, if this is open, now you will see here that there is an earthquake damage option. You select the damage option here, let's say heavily damaged. And when you come to the relevant element here, it recognizes it as heavily damaged. Now, after showing these, we have introduced our options. We can continue with the performance steps. What we need to do here now is that we had already set the earthquake to 0 here. After setting the earthquake to 0, we need to select the earthquake code from the year the structure was built. So we have selected them. 1975, Turkey, earthquake regulation, from here. After selecting this option, we need to come to the core options here. From the detail options, here, For beams and columns, we need to increase the reinforcement spacing and reduce the reinforcement diameters to be compatible with the year 1975.
Yes. First of all, if we start with the beams, there is no option. I will change on the first page. The diameters here seem sufficient for now. I will not make any changes. However, when I get to page 2, I will pay attention to selecting the maximum stirrup spacing option as 35 centimeters instead of 20 centimeters. Similarly, we have the maximum stirrup spacing option here again. I will pay attention to setting this to 30 centimeters instead of 15 centimeters. I have changed these spacings here in the beams. Other than that, there is no other option I will change here. Moving on to the column options and the column options. The minimum diameter of the column is 14, according to our latest regulation. I will reduce this to 12 for the 75 regulation. I considered it as 12. Similarly, I will consider the maximum tie spacing as 40 centimeters instead of 25 centimeters. Here again, I will consider the maximum stirrup spacing as approximately 40 centimeters instead of 20 cm. Yes, we have made these adjustments this way. We have also selected our regulation. Once we select our regulation, you can see that the data here is prepared according to the 1975 earthquake regulation, and our earthquake value is 0 here. It is clear that it is 0 from here. Yes, we have completed all our options this way. Now, to determine the reinforcements, we can analyze our structure. The world analysis option is selected here. I will use model analysis for the earthquake. There is no earthquake situation here anyway. Normally, it can be used this way. And our foundation is not modeled here anyway, since the foundations are designed as normally ductile. The performance of the foundations is not checked, only the stress coming on it is checked, and it is decided whether to strengthen it. Accordingly, here, in terms of performance, it does not matter which option you choose for the superstructure solution, or which foundation option you choose. It will solve them separately in any case, so the first option can remain selected. When we go into more detail in the performance section, I will explain the difference between linear analysis and nonlinear analysis more clearly there. Right now, our goal is to determine the reinforcement under the applied loads. I am not touching any option, and under linear analysis, I will solve the structure and here the project. This was the first modeled state. We also adjusted the management unity, etc. according to 1975. Now, according to 1975, I will save this with a different name. Yes, while saving it with a different name at first. I will save its name this way to understand what we did as reinforcement determination. Yes, I will designate the abbreviation for reinforcement determination. I can analyze it this way. The analysis is now completed. We currently go to the Structure Performance Reinforcement Arrangement tab. We click the Reinforcement Arrangement option once more, simply. Yes, look, there are options here. Now, if we want to copy the reinforcements we found as a result of this analysis, as the existing reinforcement, we need to select this option. You can also select this alternatively if you want to assign reinforcements according to the minimum Reinforcement ratio, you can choose this option. Since we do not have a new material E1, this option is inactive. Now, I will perform the assignment according to the minimum percent, and we click on this here. In front of me, regarding the structure elements, minimum percent ratios appear. I need to make an arrangement here. According to the 1975 regulation, in columns, this ratio needs to be taken as 5%. I will absolutely not touch the other elements at all, I promise. It is important for me to check these boxes here. I need to mark these elements. There is also an option related to moment capacities. We need to check this as well. The reason for this is as follows. Now, we said our structure stands under vertical loads. Therefore, in this analysis, when assigning these reinforcements, the moment carrying capacity of the relevant element must be greater than the sum of the moment carrying capacities under dead loads. 5 loads. Because our building is standing, this condition must be met. Thus, reinforcement transfer will not be ensured solely based on the minimum reinforcement ratio. According to the minimum reinforcement ratio, because if we do not check this option, and it provides reinforcement rights according to the minimum reinforcement ratio, then maybe it will only put the minimum reinforcement without providing this option. And we check this, places a more realistic reinforcement to also meet this requirement. So it doesn't just consider the minimum reinforcement ratio. Here, it places reinforcement sequences to ensure this ratio, which is a much healthier situation. Therefore, we check these options for both the shear wall, the column, and the beam. Then, when we click OK, it stores the relevant reinforcements. In its memory is a MED extension file. If you encounter issues with the reinforcement transfer, I recommend deleting the MED extension file and redoing the transfer. Now the reinforcements have been transferred. Our reinforcements are now ready. We can proceed to linear performance analyses. Here, before moving on to the linear performance analysis, there are some points where this linear performance analysis can be used. Cannot always use linear performance analysis. Are we in a position to use these? Are we in a position to perform a linear analysis? First, we need to look at this. Regarding this, I am opening the relevant regulation article. When Article 15-5-3 of our regulation is examined, 5 options are provided here. In the event that any of the conditions in these options occur, the linear analysis method cannot be applied. The last 3 options are related to eco-values. In other words, the effective capacity ratios. And these eco-values cannot be known. Without performing a linear analysis, to know these eco-values, we will first apply the linear performance analysis. Afterwards, we will check the echo values, and if the echo values are insufficient, we can say that the linear analysis is invalid. Then we will need to turn to the nonlinear analysis method. In the first 2 options, we can determine it without performing an analysis, because it is related to the building's difficulty class and whether there is B3 irregularity. If either of these 2 options exists, there is no need to directly subject the internal structure to linear analysis. If the building's strength class is less than 5, or if there is B3 irregularity in our structure, then we cannot perform linear analysis. By B3 irregularity, we mean a geometric irregularity. For example, it is a type of irregularity caused by undesirable situations such as the walls on the upper floor resting on columns on the lower floor. When these occur, we cannot apply the linear analysis method. Before moving on to linear performance analysis, I would like to provide some information about reinforcement arrangement. We have currently used minimum reinforcement. we took the reinforcements according to the minimum percentage. However, in some elements, when I go on site and conduct an inspection, I might determine the actual reinforcements there. In those elements, I might want to enter the actual reinforcements instead of the minimum reinforcement. I might want to obtain a more realistic performance result. Therefore, it is beneficial to arrange the reinforcements as well by entering the actual reinforcements of the elements you know for certain. You can obtain a more realistic performance analysis result. Generally, for the sake of convenience, if you know the reinforcement of a lot of elements, it can sometimes be tedious to input them. Therefore, in such cases, you can assign a minimum percentage to all of them and check if it suffices based on the performance analysis results. If it is sufficient, and there is no problem, even if you add more reinforcement there, it will still be sufficient. If it is not sufficient and requires it, you can continue the analysis by entering the actual reinforcements on the insufficient element. This provides more convenience. This is an easier way than entering the reinforcements of all elements one by one. Here, I will assume that we already know a few of them, and I will now show how to enter them. For this, we need to reach the analysis results here. We reach the analysis results, and once we do, we click the performance arrangement button again. We can arrange the reinforcements, either on an element basis or collectively. First, I would like to start with the reinforcement arrangement button here. We can make adjustments on an element basis. Here, for example, when I come to column 102, it shows me the reinforcements that have been placed. I can go and change them on site. From here, I can adjust the stirrup, ties, and can also re-enter the corrosion rates onto the relevant element. And of course, I can apply these to the upper floors, as well in the continuation of the same column on the upper floors. For example, 2514, say, 516 was used there. I am making changes here in the same way. Let it be 516 on all floors. You can make individual adjustments on the relevant element. You have the option to make adjustments collectively. As well, when I click OK here, it assigns the existing reinforcements accordingly. You can view it again by clicking on the relevant element. Of course, you can also do this for the column's beam. For example, at the entrance of 102, if the assembly reinforcement is not 2512, we can say it should be 2514. 100. The reinforcement might have been placed in the same way. For the relevant elements, arrangements can be made in this manner. Instead of being placed at intervals of 25, for example, it might have been placed at intervals of 20. We can adjust it this way. After adjusting these, they are automatically saved to the file with the .mat extension. Additionally, if you want, you can save it again from here. When you press it, it will save, and these will be backed up in a file with a .mat extension. Besides this, we have a reinforcement copy button. Here, we need to select the relevant element. Which element do we want to copy? Is it a beam, a column, or a panel? For example, let's choose the beam. It takes the reinforcement of this beam. Here, we can directly copy any beam we want. Now, for example, we took this and we copied it here. Copies can be made in this way. Of course, we can also do this on columns. For example, we took column 104 and copied it to column 105. Then we took 104 columns again. For example, we copied them to 119. This way, copying can also be done on the same plan. We have a multiple reinforcement arrangement button. When we click on the multiple or selective reinforcement arrangement button, it asks us to select our element type. Again, here, if you want, you can also select all elements. After selecting these, I will again take into account the elements. Not just beams, not just columns, not just panels, but all of them, and I select them. Here you are setting this option, and if you press the Select All button here, you will have selected all the elements on the entire floor, or you can click on the window selection here. Then you will have selected only the elements that you will include in the window. Right now, since everything is selected, you can't see this clearly. Here you can proceed as you wish. Instead of all of them, you can choose just the beam or just the column. You can also select these. For example, let's say you remove that part. Let's select only the beam option. Should choose the sill that we took to the window, and we take it this way. Yes, I only selected the limes here. And after selecting these, look, it gives us the option to copy the reinforcements to the other upper floors as well. For example, take the reinforcements here, you can copy them to a single floor or to all floors if you wish. You can plan it this way. Here, reinforcement arrangement can be carried out in this manner. Yes, after that we can exit from here. The reinforcements have been backed up. Again, it is ready in its final form. Now we can perform the linear performance analysis here. Here we provide the first two options to perform linear performance analysis. Our building class 3 is not less than 5 but 6. Our earthquake design class is 2, and our building usage class is also 3. Therefore, since our earthquake design class is 2, we will only check our structure with the normal performance target. Here, you will only check it under DD2. We don't need to aim for any advanced performance targets. We will solve it under DD2 first. We will solve it linearly. Then, of course, we will check if the other three options there are met, meaning the eco values. If that is ensured, we will say that the linear results are valid, and if we provide the necessary performance assistance as a result of the analysis, the analysis will be complete. If not, we will of course perform reinforcement. Or if the eco values are not valid, then we will move on to nonlinear analysis. And we will perform a nonlinear analysis to see if our performance is sufficient. If it is not sufficient, we will proceed to the strengthening phase. Now, since we will be looking at the linear performance analysis here, I am saving it again with a different name.
And now that our reinforcements have been determined, it is, of course, important that these options are selected in the performance options. The options here will now gain significant importance. We had already determined these. We need to change the earthquake regulations here. Now, we created the 1975 regulations to determine the natural parameters. We have already determined them. Now, I want to conduct a performance analysis according to the 2018 Turkey building earthquake regulations. Therefore, I am choosing this first option. We have determined these. Now, after determining these, our reinforcements are also clear. We have set our options. We have saved them. And, of course, the earthquake is very important. From now on, we will conduct performance control under the earthquake. Here, we will take the R value as 1. Currently, we do not have any strengthening elements. There is no situation that requires us to take 4. If there are no strengthening elements, whatever you take in the background will be taken. It will be considered as 1. The R value of 4 is taken only to determine the directions of the strengthening elements. Since we are not doing any strengthening right now, we will only look at the performance. I considered it as 1. Yes, these are the options here. And of course, the most important thing will be to determine our earthquake. We will determine our earthquake from here. We need to identify the location of where the building was constructed.
This is important. This was the last location I determined, and I took it into consideration. Here, my STS is 0.70, which means our earthquake design class is 2, because it falls between 0.50 and 0.75 for the DD2 earthquake. This is how we determined it. We have also assigned our earthquake. Our structure is now ready for performance. We can save it again and perform the performance analysis on our structure. Yes, our performance analysis is complete. Now we can examine the performance report in detail from here. When we examine it in detail here, the detailed results of all calculations made according to the regulations are shown here. Finally, when we come to the building performance part here, the brittle elements that have shown brittleness are provided. Stress has been observed in some columns. This stress issue arises due to the shear safety of the column entry join regions. These need to be corrected. Even if you meet the necessary performance condition, you will achieve the required performance once you correct these issues. It can be seen below that the controlled damage performance target has been achieved. The regulations already require us to achieve controlled damage. When we look at it, we can say that the redundancy condition is solid if we repair the damage in the relevant elements. However, there is a very important point that we need to check here. As I mentioned before, we need to confirm whether this linearity is valid. We need to do this with echo controls. And when we go down, you can see that echo control has been performed for the beams here. COCO inspections are being conducted on the floor, similarly within the columns as well. Of course, they are being done, and in the end, the program informs us whether the eco inspections are sufficient. When we come to the last option, as seen here, you can see that the beam eco values are almost all greater than 5 throughout the entire floor, and this needs to be less than 5. While the columns meet the eco values, the beams do not, and therefore our Dinar analysis results are not valid. And as it is written below, we need to perform the relevant performance analysis using the nonlinear analysis method. Linear analysis is not sufficient. I would also like to mention this here. We will use nonlinear analysis. However, there is a situation like this. Sometimes, very low quality concrete is used in some buildings, or if the directional diameters are very low and you cannot resolve them with linear analysis, trying to resolve them with nonlinear analysis is not a very correct approach. It would be much healthier to demolish and rebuild such structures. Do not try to save them with nonlinear analysis. Now, since the linear analysis results are insufficient, we will switch to the nonlinear analysis method. For this, we go back to the building information entry section. This time, I will save it under a different name again. Yes, I am recording it as a nonlinear analysis. All our necessary parameters, regulations, and earthquake details are already specified. I will just select the nonlinear analysis option here. There is no need to check the incremental model analysis option. This is a method that remained in the 2007 regulations. We are doing analysis according to 2018 Turkey building earthquake regulations. No need to check this. The STA nonlinear analysis option must be selected. The program will perform the analysis method as nonlinear analysis in this way. If you are constructing a high-rise building, then you must definitely perform the analysis with STA perform, as you need to solve it using a nonlinear analysis method in the time domain. You can use STA perform for the analysis in the detailed analysis of any type of structure. However, if there is a tall building, we definitely need to select the STA performance option. In other words, if your building is tall, this option should be selected. Apart from that, there is a single mode NAND in our analysis option. Here in the earthquake analysis, there is also a multi-mode NAND in our analysis option. I will start with the single mode first, but there are two important rules that the single mode must comply with. This is also written in our relevant regulation. If we examine the regulation article here, in Article 5622, two options are presented. One of them, the torsional irregularity coefficient, calculated based on linear elastic behavior, without considering additional eccentricity, on any floor, must be less than 1.4. In the other option, the mass participation, in the dominant vibration mode calculated based on linear elastic behavior, in the considered earthquake direction must be at least 0.70 in both directions. In other words, 70% participation is required, of course, in the calculation of this dominant vibration period, and the control of the total building mass participation. The masses of the basement floors surrounded by rigid walls should be disregarded. During these checks, when done this way, a relevant mass participation in the dominant period direction must be at least 70% in both directions. That is, the mass participation in the dominant mode in the X direction will also be 70% or higher. In the Y direction, the mass participation in the dominant vibration mode must be above 70%. And here, while considering these masses, of course, while taking into account these mass participations, we will perform our calculation without considering the masses of the basement floors. A check will be carried out accordingly. These two conditions are met, the single mode can be used. If we cannot meet even one of these two conditions, or rather, we absolutely need to meet both of them. If we cannot meet either or both of them, and we need to use the multi-mode pushover method. So we need to select the multi-mode analysis option in this case. And we need to conduct this analysis with an expert related to the subject. If we are performing a multi-mode analysis, you need to carry out these calculations under the supervision of an expert. However, for single mode, there is no need for an expert. If you meet the conditions, you can choose the single mode. I have also chosen the single mode right now, and I will check if I meet the conditions as a result of the analysis. Yes, we have already saved it this way. Now we can analyze our project. I am saving it again. Yes, our analysis is complete. We have obtained the controlled damage state. However, we need to review the analysis report upon reviewing yes. We see that the relevant new regulation clause is not fully met here. The mass participation in the X direction is below 70%. Mass participation under the dominant period, therefore, we cannot use the single mode method. We need to switch to the multi-mode method. In the Y direction, however, it is above 70, and the torsional irregularity coefficient is also less than 1.4. Since it does not meet this check in the X direction, we cannot use this method. Therefore, we are quickly transitioning to multi-mode analysis, because the single mode analysis results are currently invalid. Yes, this is also in the options. We selected the multi-mode option. And again, we are saving it this way. And we analyze again. Yes, our analysis is complete. Now we will obtain the actual analysis result. From here, and based on the result of the analysis here, we will have information on whether reinforcement is needed. Now I am coming to the direct building performance section. Yes, seen here, for the D2 earthquake we have achieved limited damage, performance. We have more than met the required performance. This point, however, there is a condition here. Since our elements are brittle, they need to be strengthened. By strengthening them, we will fully and completely meet this requirement. We have currently met the requirements, but if we do not strengthen the elements here, the necessary performance will not be achieved. Now, let's look at which elements need to be strengthened. As seen here, 113. The column. Columns continuing it on the upper floors. Due to the shear safety of the column beam joint, a ductility error occurs. Similarly, in the beams as well. 107. It continues in the beam and, of course, in the upper floors as well. There is a brittleness error. Now, we will reinforce these since this situation only occurred in certain columns. I will resort to jacketing the columns. If you want, you can also add FRP. I will show you how to do it in a moment. We do not have the option to strengthen beams with FRP. When such situations occur in beams, we can add strengthening walls, thereby to transfer the excess load from the beams to these walls, because the most effective elements during an earthquake are the rigid walls therefore. When we add strengthening panels to the strengthening wall, these panels will absorb the effects on these elements. In this way, we can prevent the beams from being overloaded. We can also reinforce our columns. Alternatively, we can add FRP, or when we add a strengthening component, it can ensure that it also absorbs the impact on the columns. I will show how to do jacketing and FRP on the columns similarly, for the related beams as well. I will create reinforcement walls instead of them. By breaking them, I won't affect the surroundings. I will directly break them and place the rigid wall for reinforcement that way. And in this way, I will resolve the structure with a linear analysis to determine the reinforcements of the strengthening walls and jacketed elements. Our structure will now be a new structure because it will have strengthening elements on it. I will check its performance again as a result of the linear analysis. If it does not meet the requirements, I will check the performance again with linear analysis, and I will understand if there are any brittle elements. I will check whether it meets the spread performance condition and complete the performance analysis. Now we return to the structure information entry section. As seen, there was a problem with our 113 columns. Here we will reinforce the 113 columns. First, let's save our project. Yes, we have recorded it now. How will we add the logic? When we right-click on the relevant element, with the mouse, 113, we click on the column information. On the far right, you have an option to add FRP. Next to the load section, and you click on this, you can select the FRP option you want. You can choose the jacket option. Here, we determine the jacket thickness. We will select 15 centimeters and the type of jacket. Of course, whether the jacket should be applied on all 4 sides or just 3 sides needs to be decided. For the jacket to be effective, it is beneficial to apply it on all 4 sides. In other words, having a jacket on 2 out of 3 sides is not very effective. Here, I will choose the option of having a jacket on all 4 sides. If we wanted to add fiber reinforced polymer, FRP, we would select our type of FRP here and choose how many layers to wrap. And then we would press OK. One important point to note here is that when wrapping with fiber reinforced polymer, FRP, we should not apply more than 2 or 3 wraps. It doesn't make sense anymore. You can apply at most 2 or 3 wraps. FRP contributes to shear in columns. And you can think of it as if you have added more stirrups to the column. It has that kind of effect in our related column elements. Due to the stress caused by the shear control of the column beam joint, using fiber reinforced polymer, FRP here, will not be very beneficial for us, because fiber reinforced polymer, FRP, does not contribute to the shear safety control of column beam joints. Therefore, the most logical approach here is to use a jacket that surrounds all 4 sides. Here, when I click the confirmation, yes, we applied our jacket. In this way, we will copy this to all floors. I am coming to the column section. Then, we select the relevant column. I want to copy it to all floors when applying the jacket. It is not always done on a single floor. The jacket should continue throughout all floors. The necessary reinforcement is already present in the relevant columns on all floors. But even if it weren't, this jacket would not be applied to just one floor. It always needs to continue up to the upper floors. That's why I am selecting all floors here, because we have 5 floors. I performed the copy from here. Yes, our logic has now been realized. Yes. Here, you can view these on all floors. We have assigned our jacket. As seen, when we come to the performance section, the jacket appears as E1 material, since it has just been assigned as E1 material. Now, I will convert the relevant beam element into a panel here. To translate this, I am selecting the panel option here. When I marked this, it was converted to a panel. The header regions of the panels are very important. The header regions are either existing columns for the panel walls or are designed within themselves. Here, we actually have an existing column, and we have even applied a jacket to it. But the existing column is normally insufficient. An existing column must be at least of C25 concrete quality to serve as the header region of the new strengthening shear wall, i.e., that panel element. Similarly, the reinforcement percentage must be more than 1%, and there must be regions with stirrup densification. The concrete quality of our existing column is already C15 concrete. Therefore, it does not already meet the necessary condition here. When it does not meet the condition, you will either create it here yourself. Add a new element to the header region here. You can design the header region yourself, or as a result of the analysis, there is no column here, for example. There is no small column either. It will automatically add the header region here. Or there could be another option. This column was already a problematic column and had been jacketed. Since the column was jacketed, our column was strengthened. And this strengthened structural element can be designed as the header region of the related panel. This is also an option. Yes, in this way, we have defined the header region. On the left side, there is no existing column. It will already create any kind of header region within itself. If you analyze it, you will see that it has already assigned a header within itself. However, as I mentioned, you can define the header region as a new element yourself. Here, I will assign a small column using the one material and determine the dimensions of the header region myself. Since it is also jacketed on the right, I will consider this strengthened column element as the header region. And of course, this element will now be a new material. Therefore, I will choose its material as E1 instead of E2 here. Yes, I assigned it as E1. Now I will assign another small column. The program will also assign it as E1. Here, I will select a 30 by 50 column. A header region with dimensions of 30 by 50, and I will carry out the assignment here. It's up to you to determine the size of this header. If you want, you can assign a slightly larger header. Yes, like this. I assigned the header as 30 to 61, or as you prefer, depending on the situation. You can also change the B2 value. Yes, I assigned such a title. When we get to the performance section, it already shows as E1 here. Our jacket is E1, the existing column is E2, our panel is E1, and here the header region I assigned is also E1 again. Now, of course, while installing these panels, the architectural project is also very important. Let's say there are insufficient panel elements, and you need to place these strengthening walls. You need to find a suitable location for them by also considering the architectural project. Here, to explain the logic of the program, I naturally noticed that there was a problem with the element here. I removed that element and replaced it. However, if I can't place a panel element here due to the situation, I can also place panel elements in different nearby locations, and thus reduce the loads on the beam, without removing the beam there. This is also an option. Here, it is necessary to act according to the architectural project. And here, of course, I will remove all floors and replace them with panel elements. We are now moving on to the floor arrangement section. First, to delete all the beams at once. Here, we select the option to apply to all floors. Then we come to the beam section. Here, the panel section is already closed. I just want it to select the beams. And when I did it this way, as you can see, it only selected the beams here. It did not select the panel element below and up to all floors. You can check it this way, and I approve their direct deletion. After confirming this, I will copy the panel element on the first floor to the upper floors. Here, of course, while modeling the panel element, let me mention that as well. Of course, the height of the floor is also considered here. You can change this dimension if you want. Because it will be rebuilt, you can assign different values to its width. For example, I have now changed it to 25. There is one more strengthening panel left. Now I will copy this panel element. These jacket elements have already been copied. I will copy the relevant panel element, along with the header on the left side here. I enabled the option to copy to all floors. I have now copied it across 5 floors. Yes, has now been copied. Now I will copy the panel title here from the column option. Yes, we have selected our relevant element. Similarly, we go to the floor copying option and select it to be copied to all floors. Yes, as you can see, it has been copied to all floors. From the performance section, we can also view the material properties again. Yes, we have now completed our reinforcement stages. From here, we can also view our reinforcement panels. Since I converted the beam to a panel here, it did not define the panel from scratch. I directly converted the relevant beam. That's why the walls on the beam stayed here. We will delete them. Now, yes, we call it a panel element. Yes, we only select the relevant panel. Before selecting this, let's say selection on all floors. Yes, it has now selected all the panels. Here, we will choose the dead load option. We go to the general information of the building and select the R. Value is 4. Mina came to the general meeting and chose the R value as 4. It is already written here for the special membership. It should be chosen as 4. We chose it as 4. Here we will select the linear analysis option, again because these reinforcements need to be assigned. If you select and analyze direct nonlinear analysis, you will get incorrect results. This is because the reinforcement of the newly assigned elements is not specified. We took R as 4. Accordingly, reinforcement will be assigned to these. We will now check the performance analysis, again with linear analysis. Yes, our analysis has now concluded. We are reviewing the performance report again. Yes, here we see that the damage to the relevant beam elements and column elements has been resolved as a result of the linear analysis. It has been determined that reinforcement is needed for 2 of our columns. On the 3rd floor, however, since the linear analysis results were not sufficient according to the EKA control, we are not considering these results. We will perform the nonlinear analysis again. Before proceeding to the nonlinear analysis here, on the relevant elements, look, the reinforcement assignment has been completed and we can view it now. You can see, as you can clearly see, the reinforcement assignment for the panel header region. It's programmed to be R4. Yes, here is the wrapped element. Indeed, if you want, you can also, if you so desire, edit these reinforcements yourself. Personally, from here, however, program already assigns reinforcements appropriately based on the analysis results. Therefore, you don't need to make any adjustments. But if you want, you can also make adjustments from here. Now, as a result of the analysis, we need to introduce the reinforcements obtained here for the panel element and the meshed element into the program, just as we introduced the reinforcement of the existing elements. Assigned to the relevant elements. Here, the reinforcements are actually assigned to the relevant elements, but we need to copy them because in the nonlinear analysis, all elements' reinforcements need to be determined. Therefore, we come to the performance reinforcement adjustment part here. We click on the Structure Reinforcement Arrangement option and E1 to the reinforcement of the new elements. We check the option to copy the reinforcements from the analysis result. And we do this. It is also saved even if it has a MET extension. And thus, now our structure that is ready for nonlinear performance analysis and the reinforcements of all elements are now copied, both new and existing elements. After completing this process, we are returning to building info entry. After performing the editing process, I am considering the R value as 1 again. After doing this, I select the nonlinear analysis option again here. First, I select the single mode finish analysis. Then, based on the analysis results, I decide whether I can use the single mode finish method. If I do not meet the necessary conditions, I switch to multi-mode and update the result of the nonlinear analysis. If the analysis results show that no elements need reinforcement, and the required performance target has been achieved, then the performance grades are met. We conclude the analysis and can say that the performance of the building is sufficient. However, if the necessary target is not achieved as a result of the performance, or if the necessary target is achieved but there are still brittle elements, then we need to continue with the reinforcement and repeat the same steps. If reinforcement is needed again, we will add the elements and determine their reinforcements using linear analysis and copy the reinforcements. Then, if there is still insufficiency after the linear analysis, and the additional control is insufficient, we will try to reach a solution, again with the nonlinear analysis. Here, I tried to show how reinforcement is done for demonstration purposes. In a real project, of course, it is very important to perform the reinforcement correctly. There are many details. These need to be taken into consideration. Where do we need to add these reinforcement panels to be compatible with the architectural project? Where can we add them? These need to be planned. I was just trying to show the logic here in a real project. You need to place the reinforcement panels correctly in the right places. And of course, where the building allows, you need to place them where possible. As I mentioned, we can apply mantling, or FDP, to the necessary columns of the architectural structure, and in this way we can ensure adequacy in the relevant columns, already as a result of the linear analysis. This column here, we had seen that its crispness was gone. The general logic is also like this. You can perform your performance analyses and reinforcement processes according to this logic. Yes, I have already conveyed the general logic to you here. To avoid the video from becoming excessively long, I will not reapply the solution in the nonlinear analysis here. However, it is necessary to continue with the logic I mentioned, here as well in general. This is what I can say about this topic. Before I finish my video here, there is one last topic I want to mention. You can also add FREP to the panel elements in the program. Of course, I am talking about the existing panel elements in the structure. I am not talking about the ones I added as walls to my forces. If you have an existing panel here, you can also add FREP to it. For example, when you come to arrange the floor here, you select the panel option here. When you come to the General Information Change section here, you will see it says FRP number, and you can select and add the type of FRP along with the number of FRP layers. You can apply the same cladding process done on the columns to your existing panels, as well as to your polygon columns. These types of different reinforcement methods are available within the program. Yes, these are my remarks regarding performance analysis and reinforcement. Thank you very much for listening to me. I wish everyone good work.